Welcome to The Explainer. Today, we're jumping straight into what is, honestly, the deepest and probably most misunderstood mystery in all of physics, the black hole's singularity. For decades now, it's been the ultimate puzzle, captivating our imaginations and absolutely stumping the greatest minds in science.
So if I ask you right now, what's actually at the center of a black hole, you probably picture this super dense point of matter, right? Just a tiny, impossibly heavy speck sucking everything in. But the mathematical reality, the stuff actually documented in the physics literature, is far stranger, and frankly, it's infinitely more fascinating than just a heavy dot in space.
Because here's the thing. To physicists, a singularity isn't really a thing at all. It's not an object you could reach out and touch. It's actually a phenomenon known as geodesic incompleteness. Think of it kind of like walking right off the edge of a map in an old video game. The trajectories of particles simply can't be extended any further in time or space. The very fabric of reality literally just falls off the edge. Okay, Section 1, the dark star origins, Newtonian gravity, and escaping light. Long before anyone ever uttered the phrase black hole, this mystery was already brewing. Way back in 1783, British clergyman John Michel, and a bit later Pierre-Simon Laplace, used Newtonian physics to imagine what they called dark stars. At the time, light was thought of as these tiny corpuscles. They figured, hey, if a star gets massive enough, its gravity would outpace the speed of light, trapping those corpuscles completely. It was a brilliant leap, and it perfectly set the stage for Albert Einstein's revolutionary 1915 theory.
Moving on to Section 2, Einstein's broken space, the mathematics of extreme gravity.
General relativity completely changed the game. It linked gravity directly to the geometry of spacetime. And it didn't take long for the math to get wild. Just 1 year later, in 1916, Carl Schwarzschild found an exact mathematical solution to Einstein's equations. And amazingly, he did this while serving on the Russian front during World War I. He solved it for a perfectly spherical, uncharged, non-rotating mass. But in doing so, he uncovered a bizarre breakdown in the math itself. This gave us two distinct concepts that totally confused physicists for decades. On the left, Schwarzschild's math predicted a coordinate singularity. Thanks to later work, we now know this is simply the event horizon, a one-way boundary you could actually cross without feeling anything special in that exact moment. But on the right side, at the dead center, radius 0, we hit a physical singularity. Curvature goes to infinity. The math doesn't just get a little weird here, it literally explodes. Which brings us to Section 3, the inevitable edge, Penrose, Hawking, and the singularity theorems. For the longest time, heavyweights like Einstein and J. Robert Oppenheimer heavily debated if this mathematical nightmare would ever happen in a real star's collapse, or if it was just some quirk of doing perfectly spherical math. Well, in 1965, Roger Penrose dropped an absolute bombshell. He proved that singularity formation doesn't even need perfect symmetry. If gravity gets strong enough to form a closed, trapped surface, a singularity is absolutely inevitable, no matter how wobbly or imperfect the dying star is. Later, Stephen Hawking joined forces with Penrose, and their combined singularity theorems showed us something really profound. A singularity isn't some dense object hiding in the dark. It is a robust, flashing warning sign that classical general relativity ceases to be able to extend certain geodesics. Basically, it's proof that classical physics has hit a brick wall. It's reached its absolute limit. Let's dive into Section 4, the information paradox. When quantum mechanics enters the fray. Because the story definitely doesn't end at that classical limit. When quantum mechanics shows up, this breakdown turns into a full-blown crisis. In 1974, Stephen Hawking made a totally shocking discovery. Applying quantum field theory to curved spacetime, he realized black holes aren't completely black. They actually emit this faint thermal glow. Meaning, over a long enough timeline, black holes slowly evaporate. These equations right here are absolutely beautiful. For the first time ever, they bridged gravity, thermodynamics, and quantum theory. They showed that a black hole actually has a microscopic temperature and that its horizon area is directly tied to its entropy. It was this massive, elegant unification of science. But, and this is a huge but, this brilliant discovery creates the notorious information paradox. See, quantum mechanics demands that information about a system's state can never, ever be destroyed. That's unitary evolution. It's kind of like burning a book. In theory, if you perfectly collected all the smoke and ashes, you could piece that book back together. But if a black hole evaporates purely as featureless thermal radiation until there's literally nothing left, the book you threw into it seems to be permanently erased from the universe, and that is a huge problem.
So, how do we fix it? Section 5. The Quantum Gravity Frontier, Modern Proposals and the Search for Truth.
The apparent destruction of information kept theoretical physicists up at night for decades. It kicked off a massive rush to rescue the fundamental laws of physics. Today's theoretical frontier is just wild. We've got holographic principles, string-theoretic fuzzballs suggesting black holes are just tangles of strings without a classical interior, loop quantum gravity replacing singularities with quantum bounces, and even mind-bending ideas like entanglement creating microscopic wormholes.
Now, probably the most influential proposal on that whole list is Juan Maldacena's ADS-CFT correspondence from 1997. It puts forward this incredibly powerful mathematical duality. Think of it like a 3D hologram being perfectly encoded on a 2D surface. Because the boundary theory mathematically preserves the information, it gives us super strong theoretical evidence that information inside the black hole is actually saved, even if, we don't fully grasp the exact mechanism of how it works in our specific universe quite yet. And this comparison perfectly captures exactly where we stand today. The classical view sees the singularity as this terrifying physical divergence, a point of infinite gravity. But the quantum view, it sees the singularity simply as a boundary, a signpost, really, demanding a new underlying microscopic structure that we just haven't mapped out completely. Ultimately, modern academic synthesis hits the nail on the head. The singularity is really just the edge of our current scientific map. It's a limitation of the mathematical tools we're currently using, not an actual monstrous point-like object lurking out there in the dark. Which leaves us with one massive lingering question. Once we finally crack the code of quantum gravity, once we can finally peer beyond that mathematical breakdown, what profound new reality is waiting for us out there? Finding that answer isn't just going to solve a math problem. It is going to fundamentally redefine our entire understanding of the universe. Thank you so much for joining me on this explainer. Keep wondering and keep looking up.